We look at these kinds of functions, okay? They're super complicated. So like look at the equations. They don't fit that x minus h, a, k. This is nothing that we can graph using transformations, all right? So when it's a fraction and you have your own polynomial in the numerator and a separate polynomial in the denominator, our approach is going to be just to start by listing all of the information that we've figured out about these different functions. So that means if there's asymptotes, if there's holes, and what the intercepts are, okay? So asymptotes, intercepts, and holes, we want to make a list of all of those possible things before we do anything else. Does that make sense to everybody? So every time we approach one of these problems, next to it, I'm basically going to set up this list. So I want to know, are there like vertical asymptotes, horizontal asymptotes, oblique asymptotes? I want to know if there are any holes, and I want to know if there's an X-intercept or Y-intercept, okay? So this list, if you're like, where is she getting this list, is the same chart that we looked at yesterday. Is that okay with everybody? And is everybody okay with my abbreviations? You're going to be writing it a lot. You don't have to use my abbreviations, but you're welcome to. So all of the VA, HA, OA are asymptotes, right? Horizontal, vertical, and oblique, okay? Then holes, X-intercepts, and Y-intercepts, all right? So asymptotes, okay? There's two up here where like they are mutually exclusive, so to speak. If you have one, you don't have the other. Remember our like the graphs that we looked at yesterday? All the ends of the graph either went horizontal or they went towards infinity and negative infinity, right? And which of the asymptotes tell us about that end behavior? Which asymptotes did we say? These asymptotes are specifically for end behavior. They're only important to guide the ends. Emily? Good. So horizontal asymptotes are one. What's the other one? Stefan? Oblique asymptotes, which means you can't have both. You can't have ends that are horizontal and then say they go towards infinity or negative infinity. So that means with these two right here, one of them is none, and one of them is an equation of something, okay, that we follow. If it's horizontal, it's an equation of a horizontal line. If it's oblique, it could be technically an equation of anything that goes off towards infinity or negative infinity at the ends, okay? How did we say yesterday we would tell if we had a horizontal or oblique asymptote? What did we focus on yesterday? We would look at what part of the equation? Morgan? Emily's enthusiastic today. Yeah. Okay, good. So the degrees, right? So look at part A, the one we're working on right now. The degree of the numerator is 2. The degree of the denominator is 3. So the higher degree is in the denominator. In that situation, how did we say we can determine, well, first, is there a horizontal asymptote in that situation? Yes, so at oblique, I get to write none, because if there is a horizontal asymptote, my ends are horizontal. They're not going towards infinity and negative infinity, and that takes away the prospect of an oblique asymptote. Then I have to know how to find my horizontal asymptote. In this situation, when the degree in the denominator was greater, how did we say, what did we see with all the graphs? The horizontal was where? Andrew? Good, it was always at 0. Okay, this is your like favorite situation. Like it's horizontal and it's automatically at 0. Doesn't matter how crazy the equation is. If the degree in the denominator is greater, our horizontal asymptote is automatically at 0. Now, because it's a horizontal asymptote, it is a horizontal line, and I write its equation like a horizontal line. Okay, so y equals 0. All right, the next thing I'm going to do is I'm actually going to go ahead and factor my equation and see if anything cancels out for multiple reasons. If I want to graph it, I'd like it to be in simplest form. The other thing is I actually have to see if anything cancels out to identify one of the things on this list. Which piece of information from my list that I'm listing here would we identify by the fact that something cancels out, a factor cancels in our equation? Taylor? Good, the holes. Okay, remember how they were called removable discontinuities because you literally could remove them from the equation. So when I'm factoring, I'm looking to make it easier, okay, and I'm looking to see if there's any holes. So I'm going to go ahead and do that. Unfortunately, the numerator doesn't factor. The denominator does have a greatest common factor of 2x squared. I'll just look at it like that for now. That might help me out later. But nothing cancels, okay? So because nothing was removed from my equation, what do I now know about the information in this list? the holes, right? How many are there? None. Nothing canceled out. I don't have to worry about there being a hole in the graph or a removable discontinuity. Okay. All right, let's finish our asymptotes. The other type of asymptote that isn't about end behavior is a vertical asymptote, and a vertical asymptote is supposed to be about what? What is it they're marking? What is that telling somebody about our function? I'm going to ask you these questions over and over again because I want to drill into your head that horizontal and oblique asymptotes are only important for the ends. You can cross them, you can do all kinds of things. They're only there for the ends of the graph. A vertical asymptote is serving a totally different purpose. So they have the same word in their name, totally different ideas. What is a vertical asymptote there for? I see Stefan and I see Taylor. They both already told me something important. I'm hoping some other people that haven't talked to me yet know something. I see Andrew. He already told me something important. Come on, people. Don't make them carry it for you. Dylan. Good, okay? And he looked back. I don't care that he looked back. That's what we should be doing. We're trying to learn it. So if we look back there, a vertical asymptote is serving a different purpose. It is where the function is undefined. That's why you can't cross them. The function literally does not have a value at that point. Horizontal and oblique asymptotes are just to describe how we behave at the end, so why can't we cross them? There's nothing that crazy about them. But vertical asymptotes are undefined. They are literally splitting our graph into pieces because we can't plot a point at that x value, okay? And when did we say our fraction was undefined? What do we do to find vertical asymptotes? So we've done it a couple times. We did them with the reciprocal graphs, the more simple graphs, okay? We did it when we were finding our restrictions and all of our simplifying and solving and multiplying problems. Susan? Good, setting the denominator equal to 0, because if a vertical asymptote is where something is undefined and we're dealing with a fraction is specifically undefined when the denominator is equal to 0. So I'm going to use the factored form of my denominator because one way to solve something is to factor it, so I feel like it already has like a step towards telling me what it's supposed to be. So if I set the 2x squared times x plus 2 equal to 0. That means I have these two choices, 2x squared equal to 0 and x plus 2 equal to 0. And that gives me two different x values, right? From this first equation, what's the x value that solves that first equation? If you divided by 2 and then square rooted, what are you getting as an x value there? 0. So one vertical asymptote is x equals 0. Okay? But there's another one, because there's this other factor. When x plus 2 is equal to 0, that would mean that x is equal to negative 2. Okay? All right, and now the intercepts. We know how to find them. We just have to work it through in this situation. So for our x-intercept, I'm going to put some of this work right here. For our x-intercept, we set y equal to 0. And solve, technically, because it's a fraction, we're multiplying by the LCD, but there's only one fraction. So you can think about it that way. You can think about it by cross multiplying, right? But either way, if you multiply by what's in the denominator on this side, it cancels it out. And when you multiply the other side by that, anything times 0 makes 0. Now this is going to happen every time we find an x-intercept in these situations, because every equation is a fraction. That's the definition of these rational functions that we're building. So you might catch on to the pattern that really it ends up being the numerator set equal to 0 every time after we take this first step, okay? And then if we finished solving this, I'm going through the solving part a little bit quicker because I think you guys have the tools to solve it. We get to the fact where 1/2 equals x squared, okay? And we would square root it. Well, it's but then divided by the negative 2. And so then this will be plus or minus, okay, 1 over rad 2. And if we didn't want the radical in the denominator, we would multiply top and bottom by rad 2 to rationalize it, and we'd have rad 2 over 2. Okay? This is kind of a difficult x-intercept, but we'll deal with it, okay? So plus or minus rad 2 over 2. That means there's 2 of them. Okay, and then since we have to actually graph it, we kind of want an idea of where this is, and this would be a more difficult one. Okay, but rad 2 is about what? What's the square root of 1? 1. The next square root that we know well is the square root of 4, which is 2. So the square root of 2 would be somewhere between 1 and 2. Is that okay? Yeah. Would it be closer to 1 or closer to 2? 1. Okay. So I don't know, say it's like 1.3 or something like that. 1.2, something like that. 1.2, 1.3, 1.4, something in there. Okay. And then that's being cut in half. So somewhere between like 0.6 and 0.7. Okay. All right. So I don't know. So like 0.65 if you want to. I don't know. It doesn't really matter that much for what we're doing. If it was like this, I'd let you approximate it. So plus or minus, and then technically, so we would write it like this. That's the way I would write it when I'm telling someone it. And then I would, for myself, know that that's approximately like 0.6 or 0.7, so that when I go plot it on the graph, like I have some idea of what that value is. Okay. The Y-intercept is a little bit simpler, right? Because all of our equations are already written where like y is equal to something. So just look back right here and think about plugging in 0 for x. Okay, in the numerator, if we plug in 0 for x, we would get 1. In the denominator, if we plug in 0 for x, we get 0. 1 over 0 is undefined, right? We can't calculate it. So what does that mean about our y-intercept? There isn't one, okay? It couldn't be calculated, so there's none. And then what we're going to do is we're going to put all this stuff onto the graph, okay? It's just going to look like random little, like a couple of points, these dashed lines that are supposed to be boundaries for something or other, okay? So vertical asymptotes at 0 and -2 means I have these vertical dashed lines at 0 and at -2. Okay. And remember what these are. Can we cross these? No, there's literally no point. So you can't cross them, because if you cross them, you're drawing a point when x is those values, but those are there because x can't be those values. Okay. So what this tells me is how many branches are there going to be of my graph? 3. Because there's 2 vertical asymptotes, so they're going to be like one on one side, then one in between them, and then like one on the other side, split apart. Okay. The next thing I'm going to mark is my horizontal asymptote at y equals 0, which basically almost all of the dashes that I'm writing right now are unimportant. Where is this really only important to me? End behavior. So it's really only important to me here and here. I really don't care about it anywhere in the middle. I just want to emphasize that when I'm done doing as much as I can with this, the ends get close to this line at 0, like we saw yesterday when we looked at the graphs. Okay. All right, I have no holes. If you have a hole, it's actually convenient because then you get to like plot a point that's not really a point, but you know that basically like your curve would go through that. It just jumps over that. So it actually would be helpful if we had a hole because we'd have like a guiding point, but we don't. And then we have these 2 X-intercepts around 0.6 or 0.7, both positive and negative. So one like right here somewhere and one like right here somewhere. All right, that's all the information we got. And we're supposed to be able to sketch what this looks like. Okay? Kind of like a little problem, right? So we're actually going to use a strategy we used before. Do you guys remember when we were solving quadratic inequalities and we drew the little number line and we split it up with intercepts and we said, oh, on this side it's positive, but then on here it's negative, so that we just kind of plugged in numbers but didn't even really have to do a full calculation. We just got to determine like positives and negatives. We're basically going to do the same thing here, okay? So just to give you an idea, let's say I was graphing over here, okay? And that this x made a positive y. Let's say I plugged it in. I'm not saying that's true. Let's just, okay, try. If I was up here, when could I cross, if I wanted to get down here, if I wanted to have negative y's, okay, can that happen based on our information over here? Okay, no, not because of this. This doesn't matter right here, right? This only matters for the ends. But what would I have to have here if my graph crossed over and then became negative? What have we marked on the graph that would have to exist over here if on this area I went from positives to negatives? Sydney? An X-intercept, right? Do I have one here? No. So if on this side of the asymptote I got one x gave me a positive y, guess what? All the x's must give me positive y's. Do you see why? They can't cross over and be negative, okay? But then there's an asymptote. That asymptote totally ends one portion of the graph, right? Remember how we did like Mario Brothers style the other day, and then you're like teleported to this other branch of the graph, right? So let's say this one was up here. Does that tell you anything about how the graph's going to behave on the other side of the asymptote? No. So once there's an asymptote, it's like new portion of the graph, it could have y's up here or it could have y's down here. But in this section, in this middle area between the two asymptotes, can it cross the x-axis? Yes, because it has an intercept, okay? Then this ends that branch and I got to completely start a new one over here. And again, its behavior will be the same until maybe it hits the x-intercept. So the important parts for me to analyze behavior, where behavior can change, it can either change by crossing through the x-axis, right? The graph can get from up here to down here by literally crossing through. So x-intercepts are super important. The other way the behavior can change is that one branch completely ends, and when I start a new one, it can start in a whole different place, right? So the vertical asymptotes and the x-intercepts are sectioning my graph into different pieces that I have to analyze, okay? So when we do the analysis, I would draw an x-axis just like we did with our quadratic analysis, but this time, instead of just splitting it up with x-intercepts, I want the x-intercepts, but I also want the asymptotes because they completely break into a new section of graph. And when I say asymptotes, I mean the ones that break the graph apart, which are the vertical asymptotes, okay? So we had a vertical asymptote at -2. We had this x-intercept at approximately -0.6 or -0.7. We have this other asymptote at 0, and then we have another x-intercepts at approximately 0.6 or 0.7. So how many numbers do I have to actually test to see what's happening? I need to test an x over here to see if it gives me positive y's or negative. Then I have to test on the other side of the asymptote. But I can't just test once between these asymptotes because it might hit this and turn back around, or it might hit this and actually cross through the axis. So I have to test 1 section, 2 section, 3 section, 4 section, 5 sections, okay? 5 different values, okay? So when I say 5 different values, if the first value is coming from this section right here, that means I am saying pick an x that is smaller than -2 and just tell me when you plug it in, does it produce positive y's or negative y's, okay? Points above the x-axis or points below the x-axis. I don't really care the number, so don't get hung up on the number. So let's say I plug in -10, okay? When I plug -10, I'm going to use the factored form because I think it makes it easier, okay? When I plug -10 into the numerator, -10 squared becomes a gigantic positive number, right? But then it gets multiplied by -2, which makes it a super negative number, plus 1 will give me a negative. So my numerator will be negative when I plug in -10. Is that okay with everybody? Now I'm going to try plugging -10 into the denominator. In the first part of the denominator, -10 squared would make a positive, and a positive number times 2 is still positive. But that's going to multiply this quantity right here. -10 plus 2 would make a negative, and that negative times that positive would make a negative. So I would have a negative in the numerator, right? Okay. Over a negative in the denominator, which overall would make a positive. So what I know is that no matter which number you chose, -10, -100, -3, -2.1, you end up getting positive values for all of those x's. Now, I'm going to draw something that is not necessary on your graph. I think it's just going to help us the first time that we visualize this, okay? So you don't have to draw this part. But what that's telling me is that on my graph, these x values only produce positive y values, which means I'm only allowed to sketch graph here. There's no x-intercept, so it can't hit the x-axis. Whatever is over here only exists in that area. Is that okay with everybody? All right, now let's go to the next area to see what happens. Okay, So the next one, we don't even know exactly the decimal, but that's okay. We'll just pick something really close to -2. Well, we could pick -1, right? Because it's in between them, and that's not bad. So let's plug in -1. -1 squared is +1 times -2 is -2 plus 1 is a negative. So negative in the numerator. In this, it will make a positive. This will always be positive. Is that okay with everybody, the 2x squared? Okay. And then -1 plus 2 would make a positive. So in the denominator, we have positives. In the numerator, we have negatives, which overall would end up producing a negative. Okay. So that means all of these x's give me negative values. And what that means on the graph is that in between that asymptote and that x-intercept right here, sorry, I shouldn't have hit the x-axis, I can only graph below the x-axis. Is that okay with everybody? So this highlighting is not necessary, but it's what you should be thinking in your head. It's what your analysis means. You're only allowed to draw stuff there, not up there, okay? So then between these, I'll just pick something really close to 0, but on the negative side. What value do you guys want to use? What do you got, 0.5? Do you guys like 0.5s? Is that your thing? Okay. All right, -0.5. So -0.5 squared, this is so hard, okay? I'm going to use it like a fraction. -1/2 squared is 1/4. 1/4 times -2 is -1/2, right? And -1/2 plus 1 would be a positive. Are we okay with that? So positive in the numerator, okay? This one's always positive, okay? And then something like -1/2 plus 2 would be positive. So I got like positives all around, is that right? So overall, this will be positive, which means every x value here produces positive y values, which is trying to tell me that on the graph, when I go to sketch it, in this section between that x-intercept and this new asymptote, I'm only allowed to graph up here above the x-axis. Okay? All right, next number. A positive 0.5 instead of a negative 0.5, okay? All right, so when we plug that in, so whether this was positive 0.5 or negative 0.5 is going to work out the same way because we square it and then multiply, and that was a positive last time, right? So positive, this is positive. Positive plus 2 will still be positive. So again, all of them turn out to be positives, which means between that asymptote and that intercept, right here, these x's only give me positive y's, which means on the graph, the points would only exist above the x-axis in that section. Should be like here. Okay. We're almost done. All right. Okay, one more thing to test. So we could pick like positive 10, right? Something, anything above that value, this 0.6 or 0.7. So when we plug in something like positive 10, we already did something similar to this. This makes like 100 times -2 makes really negative number plus 1 will be a negative in the numerator. This will be positive, and a positive plus 2 will be positive. So we'll have a negative over a positive, which overall produces a negative result. So these x's make negative y's, which mean after that x-intercept, my graph can only be graphed below the x-axis. Is everybody okay with how, number one, how I'm doing that analysis? Okay, what I'm doing. Number two, like why we're doing it, which is why I'm highlighting right here, which I said is like not necessary, but I'm trying to show you the relationship of why I'm doing it. When we first stopped and I said, now we have to sketch it, like I don't know where the graph goes. Now I at least have some ideas of where I'm allowed to draw pieces of the graph, right? And then we're gonna use what all the things on here mean, and we should be able to get a sketch of this graph, okay? So remember what this means, our horizontal asymptote. It's there for end behavior, meaning the end of our graph gets flat like 0. It doesn't actually reach 0, but it gets flat like 0. And it either does it from right above 0, right? It starts looking like 0, or right below 0. In this case, based on what we've tested and where we've highlighted, when we start to look like 0, will we be below 0 starting to look like 0, or above 0 looking like 0? Above, right? So I know whatever happens in this graph, it ends up kind of being like this. Almost at 0, not quite, but from above because no points can be below. Okay? Then look at what you guys saw yesterday. What happens when you get really close to a vertical asymptote? What does the graph do? Does it just abruptly stop? Like, I just stop right here. No, right? It actually gets, math is weird, right? Infinitely close to that number without ever reaching that number, right? Okay, so we have to get infinitely close to this vertical line. The graph basically started to look like the vertical line, right? And there's two ways for us to do that. When we get close to it, we're either going to bend and start looking vertical upward, or we're going to start looking vertical downward. But based on what we've shaded up here and where we're allowed to graph, is this guy going to start bending upward, or is it going to bend downward? Upward, right? Because on this side of the asymptote, we're only allowed to plot points here. So I'm just going to connect this behavior that I know to this behavior that I know. My points aren't exact, but someone should know, like, it has a branch up over here that follows these things. So I'm just going to connect this somehow to that. It has to be there. Is that okay with everybody how I'm figuring that out? All right, so on the other side of the asymptote, you have the same options. It would look vertical on the other side of it too, which meant it's either looking real vertical going downward like this or real vertical going upward like this next to the asymptote. But based on where we've shaded, on this right side of this first asymptote, am I down here or am I up here? Down here, I'm only allowed to plot points down there. Okay, so the up there is not an option. Like this was an option. So I know I have behavior here, and then I actually have a point that exists on my graph. So I have to connect this behavior, eventually comes up and hits that point, right? So I'm just going to connect something that's vertical like the asymptote to curve over and eventually hit that point. Do I know if those points are exact, if it's steep enough or whatever? I don't know, and that's okay, all right? So then I hit the X-intercept, that's an actual point that exists on my graph. Do I turn around and go back down by this asymptote, or do I go through and go up by this asymptote? Through, because my analysis told me that after this intercept, I only had positive y values and I'm only allowed to graph up here and not down here. So now I'm going to connect that point to this behavior that's getting vertical by the asymptote going upward like that. Okay. All right, then there's our asymptote, completely disconnects our graph. We move to the other side of the asymptote, and every time we're next to a vertical asymptote, we know we either curved up next to it or down. So my choices on this side of the vertical asymptote are that my graph either goes up looking vertical or comes down. Okay. Based on our analysis, look where we highlighted, just to the right of that asymptote, we highlighted positive y values, which means this would be impossible, right? And so we must have this behavior up here. And then notice what comes next. What comes next is a physical point on our graph. So we're going to connect that behavior to this point that we know we're supposed to hit. And then we're going to decide what happens after that point. Does the graph turn around and stay in the positive y values, or does it come through to the negative y values? Comes through, okay? So it definitely goes through, and then I'm just going to kind of go like that for a second, because what's supposed to happen at the end of the graph? Because there's no more intercepts or asymptotes, right? I'll just get to the end. But the end is supposed to behave like 0, right? So it comes down here. I don't know how far. I don't know if it's close or what. But eventually, it's supposed to behave like this guy again. Does it start behaving like this horizontal line from above it or from below it? Below it, based on my highlighting. So I'm supposed to be looking like this in a little bit. So I don't care how you make that happen. Okay, you don't have to test any points or be exact, but it's got to come back up here at some point and start behaving like a horizontal line. And I know that looks weird, but did you see the shapes that we graphed yesterday? Some of them had these little cricks in them, okay? Now, could this go way down here and come back up here? Absolutely. I have no idea. Do I care? No. I'm looking for your graph to be correct in asymptotes, intercepts, and general behavior, meaning you're plotting the branches in the right places. Okay, Jake? So remember, a horizontal asymptote is not saying the function is undefined. It is specifically there for the ends of the graph. So it technically doesn't matter any of this time It is only there. Remember the graphs that we graphed yesterday, how they were all crazy in the middle? It was just the ends that looked like 0. That's the only thing it's there for. So if it helps you differentiate for your horizontal asymptotes, don't even put the asymptote portion in here. Like, only put it at the ends, and maybe that will help you figure it out. Okay? Is this all right with everybody? Okay, we're not going to finish another whole example. Was I so right about how long this would take us? And I'm sorry if you felt like I was going really slow. I was just trying to make sure we understood why we're doing everything we're doing, because it's long. But I do want to look at the beginning of another problem. Generally, this process is the same over and over again. If you have a hole, you plot the hole just as an open point, and it's actually kind of cool because it gives you one extra point that you know to connect with your curve, so you're like a better grapher. The one that gets the hardest is the oblique asymptote. So I just want to look at that and how we would find that before we send you guys off to just watch like video examples, because I think that would be a hard thing to watch on a video. So example C would be the one that would have an oblique asymptote. And how would I know that this function has an oblique asymptote? What did I look at to be like, which one am I going to show them with the oblique asymptote? Ooh, this one. The degree, right? Okay, the degree is higher in the numerator. That means oblique asymptote. Okay, so when you make your list here of information, the horizontal asymptote would say none, and we're going to write an equation for an oblique asymptote. Okay. So what did we say to do to find an oblique asymptote? Emily? So that's when the degrees are the same. That's our other horizontal asymptote. Dylan? We just wrote it down next to oblique asymptote in the large chart. Stefan? Just divide it. So we're basically rewriting the function. Like this literally means 5x squared divided by 3 plus x. And are you guys okay if I rewrite the 3 plus x as x plus 3? Okay? So that I have it in the order that I want to see it. Okay. So 5x squared being divided by x plus 3. Can we do synthetic division there? Yeah, okay. If not, we'd have to go through the long division. But since it's synthetic, are you guys okay if I use synthetic since it's a lot shorter? Okay. So that would be a negative 3 in here because I'm dividing by x plus 3. And then my coefficients are just 5. But that's not all I can write. That's for the x squared. What about the x term? 0. And what about the constant? 0. Okay, I got to have stuff all the way to the constant or this won't work. So this is 5, negative 15, 45. All right, so that means that technically this function, if you divide it out, is the same thing as 5x minus 15 plus this weird remainder. Is that okay with everybody? Like those are the same thing, just written a different way. Here's the deal with the oblique asymptote. Since it's only for end behavior, and hopefully this will address Jake's question a little bit again, it's not for when you plug in small numbers. Like if I plug in 1, this matters because 45 divided by 4 is something that's just a little bit smaller than 15, and that's going to majorly change what my answer is right here. But think about plugging in 1 million, okay? If you plug in 1 million, over here you're getting like 5 million minus 15, and then you're adding to it this. What is 45 divided by 1,000,003? A teeny, 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 tiny number, right? Does that number now really have any effect on our million? No. So when we write the oblique asymptote, we basically ignore the remainder because it matters when the numbers are small in the middle of our function, but it wouldn't matter when the numbers get really big. So we're basically saying as the numbers get really large, this piece becomes so small and so insignificant that our function starts to look like it's just this and not this. So that's why this becomes our asymptote, because we're not exactly that, but we get really, really close to that. So our asymptote in this case wouldn't be horizontal, it's oblique. That means it's aligned with this slope. Okay, and we would literally, and I'm going to tell you in this case, it'd be best to number your graph by 5s, okay? We would literally graph the oblique asymptote like this, like a line. So we would go to negative 15. Our slope is 5. Oh, actually, I'm going to do that y's by 5, but I'm going to do the x's by 1. Okay. So I'm going to go up 5 over 1. See how I made that easy for myself? Okay. All right. make things easy for yourself if you're determining your graph of 5 over 1. So this looks like it has a slope of 1, but it really has a slope of 5. This is our oblique asymptote. Okay. And this graph would have a vertical asymptote at x equals -3. Okay. It has no holes. I'm just giving you this information because I'm trying to make it a little quicker. And the x and the y-intercept are at 0. So we would get this information like this, okay? And then just to give you a heads up, this will be on the video. I'll go back through the whole problem. But how many times would we have to split up our analysis of the x-axis? So that would be our next thing to kind of highlight where we're allowed to graph. How many places would we have to split that x-axis up to plug stuff in? Okay, so 2 places, right here and here, not here, right? Because what's the oblique asymptote for? End behavior. It doesn't split our graph at all. I can actually ignore all of this. All I know is at the end, I'm going to go towards infinity like this line. And at this end, I'm going to go towards negative infinity. So it's going to be like a weird like this, and then like this or something, okay?
So it's that like, that weird part.
Yeah.